For our next problem, we're going to optimize of the volume of a box. So what we want to do is find the dimensions of the largest box. When I say largest, I mean the box with the highest volume that can be made by cutting equal squares from the corners of a 24 by 24 inch square piece of cardboard and turning up the sides. So let's draw this actually before we get any further. So what we have here is we have a 24 by 24 piece of cardboard. This is 24 inches on each side. And what I want to do is cut out a square of size X like that. And I want to do this in all four corners so that these are all equal cuts of an X by X square on the side. And then what I'm going to do is from this I'm going to form a box like that. Let's see. We're going to form a box like this, which has no top. It only has a bottom and sides. So the thing to recognize here is that this is going to form the bottom of the box, what's left in there. So the bottom of the box is going to be, we have a 24-inch side, and we're taking two cuts of size X out of each side. So that means that the bottom of the box is going to be 24 minus 2x by 24 minus 2x. In other words, we have 24-inch side, we subtract x twice from it, thereby getting the length of this purple side, and the same in the vertical direction. So this is going to be 24 minus 2x by 24 minus 2x, because that's the bottom of the box. And then the sides of the box are just going to be these dotted green lines of length x. So what we can see is that one quantity to be optimized is the volume of the box. For two, where we want to write the objective function, we can see that the objective function is just going to be the length by width by the height of the box, and we can write that clearly as a function of x. It's, the size of the cut that we take completely determines the dimensions of the box, as you can see, since I've been able to write all three dimensions using just x. So this is going to be 24 minus 2x by 24 minus 2x times x, where this is the length, this is the width that happens to be the same, and this is the height. So simplifying that comes out to, I've already done the calculation in advance, that's going to be 576 minus 48x plus 4x squared times x, which equals 4x cubed minus 48x squared plus 576x. So there's the objective function. Now, let's find the domain. Clearly the smallest cut that I can take is going to be 0. In other words, by the least amount that I can cut out of the corner is none, so the lowest possible x value is going to be 0. The highest possible x value, since I have to take a cut of x in both directions, and I only have 24 inches to work with, I can't take a cut of 24, because then that wouldn't leave anything left over for the other side. Each side can take up at most half of the length of that side, or rather, each square can only take up at most half of the length of the side that it's being cut from. So the most that I can cut is 12. So that's the domain. And now what I'm going to do is just run the optimization procedure on this objective function on the domain 0, 12. So you see that if v of x equals 4x cubed minus 48x squared plus 576x, then v prime of x is 12x squared minus 96, not 97, 96x plus 576. This factors as follows. That's a factoring of, I'm pulling out a factor of 12 from that derivative, and now I can factor the quadratic pretty easily. This is going to be x minus 4, x minus 12. We see that 12 is already an endpoint, so the critical point is going to be x equals 4. So we have critical point x equals 4. I'm not even bothering to go through the whole thing of setting v prime equal to 0. I think everyone understands this is v prime. I'm looking for places where it's 0. There are clearly no places where it's undefined. So I'm now going to what I'm going to do is I'm going to check the volume at I want to check the volume at the endpoints. V of 0. If you look at this definition of v of x, when I've written it in factored form, you can see that if I plug in 0, then I'm going to multiply 24 by 24 by 0, which gives me 0. If I plug in the other endpoint 12, I get 24 minus 2 times 12, which is 24 minus 24, so each of these factors in parentheses come out to 0. So v of 0 is 0, v of 12 is equal to 0, and by the way, that's completely what we would expect. If I don't take any cut out of the corners, then I don't have anything to produce the height of the box. If I cut up to 12, then I remove the entire piece of cardboard and there's no box left. So in both cases it makes sense that I'd be getting a 0 volume box. On the other hand, if I plug in 4, that gives me, let's see, using this form of the expression for v of x, I get 4 times 64 minus 48 times 16 plus 576 times 4, and that equals, this is equal to 1024. Clearly that's more than 0. So the largest box is going to be made by cutting 4-inch squares out of each corner. That's going to give us, if I cut a 4-inch square, then 24 minus 2x is 16. So the dimensions of the largest box are 16 by 16 by 4. In other words, cut 4-inch square out of each corner. That's the answer.